to the 7 times the charge. So we'd all be electrically charged, and we'd all repel each other. Okay. Now, an interesting question is whether these things are static properties or actually arise from some hidden dynamics. Dynamics are cool because once you understand how things move, you understand the source of something. Where static properties are not so nice. But an interesting point is that static properties can result from dynamics. And this was first discovered about 200 years ago. And this was discovered by a guy named Ørsted. And Ørsted basically established that magnetism is the result of dynamics. And you know, I think the urban legend has it that, you know, he thought about this one evening, and the next day he did the experiment in class in front of the full audience. Okay, and what he did is he took a magnetized needle and he put a wire above it, and with the ability to run a current through a wire. Unfortunately, urban legend has it, what he did when he did this in class is he put this needle perpendicular to the wire, and he thought it would be spectacular and he would get a great applause, and he turned on the current and nothing happened. Okay, that was very unfortunate. After class, urban legend has it, he thought about it again and he said, you know, maybe my intuition was right, but partially wrong. And so he did the experiment again, but he put the needle parallel to the wire, turned on the wire, and whoop, the needle started turning. Okay? And basically what he established is that, as opposed to what people initially thought, that there is something called magnetic charge, and that's what's sitting in the little magnets that you use, stuff you stick on the fridge, or little toys that you click together, or, you know, the cover on your iPad nowadays. It turns out that what basically established is that there is no magnetic charge. And all of that magnetic charge, what looks like a static magnetic charge, just arises from currents. And when you have a little magnet, which you have at home, which you stick on the fridge, it's because inside this thing, all the little currents that are going around in all the little atoms inside this thing are all oriented in the same direction. Okay? And the net result is that you have a continuous current going, and that generates something that looks like a static magnetic charge. So, important point is that you can get, this simplified the problem, right? This basically divided the complexity of electromagnetism by a factor of 2. You didn't need to worry about magnetism anymore. The only thing you needed to understand was electric charge. Okay, so that's kind of cool. Some of these charges could potentially originate in dynamics, which would be good and reduce the complexity of the problem. Now, the next question is, yes, but wait a second. In these setups, everything is quantized, right? I see charge, you know, -1, 0, -1/3, and +2/3. This is not a continuous thing. Usually when you have dynamics at work, planets around, you know, meteors, whatever, you get a full spectrum of things. Things are not quantized. So if it arises, if it's static, you can understand that it's quantized. If it's dynamic, well, turns out this is not a problem. Because if you have dynamics and you have something which is called a boundary condition, then you automatically, essentially, always get quantization. This is actually where quantum mechanics gets its name. But this happens in the classical case, and the obvious example is the guitar string, right? Because what is the guitar string? The guitar string is a string that is stuck and it's fixed at both ends. And for it to oscillate in a resonant mode, the wavelength on that thing needs to be related to the length of this interval. It can only, because these points are fixed. So here you see that the wavelength for this is about twice. What we call wavelength is a full oscillation like this. So here the wavelength is the same as the length of the interval. Here the interval is twice as long. Here the interval is shorter, and so on. The point is that you can only oscillate in certain patterns, and you cannot oscillate a thing in between which would go up here and come back down and end up here. It doesn't work because the string isn't fixed here. And in music, you have the first harmonic, second harmonic, third harmonic, and so on and so forth. So all of this works. This is actually an image of taking pictures with a stroboscope of a real wire to which this is done. Okay, so basically, even in the classical case, you have standing waves on a fixed string, and the wavelength is fixed. only certain values are allowed. And in the quantum case, pretty much the same thing happens. And fundamentally, in quantum mechanics, particle motion is described by waves, and so the analogy with the guitar string is a very good one. Okay? And basically, if you put a particle in a box, it behaves like a standing wave on a string. The only little difference when you translate everything is that the energy is quantized instead of just a wavelength. Okay, so we can get quantization from after we introduce dynamics. So that's all good. So now, how do we approach this? Can we actually figure out whether any of this is dynamic or not?